Okay, hello everybody. Today we will be talking about basic data structures such as stack, queue, Deque, and heap. I don't know how many we will have time to discuss, but let us start from the beginning. Let's start from the stack. So yeah, last time we talked about sorting, so we were talking about algorithms. Today we are talking about data structures. So we will start with stack today. What stack is? Stack is a data structure that supports two operations: push X and pop. So what does it mean? We have a huge array that is growing upwards, and push does the following. Push adds an element to the top of the stack of this I don't know, array. So like when you make push X, then you make push Y, push Y, you put them on top of the previous one. And when you make a pop, you take the topmost element and withdraw it and return. So if you have push X, push Y, then pop will return Y. This data structure is named leaf form, which is last in, first out. So the latest element that was added to the stack is returned by pop. My first question, is it clear on how to implement this data structure? Yeah, unfortunately we don't have a huge interaction right now because we don't have Zoom, so you couldn't have the discussion. Probably we can start. Probably we can do Zoom. I will check. Yeah, how to implement the data structure. Okay, let me try to create a Zoom so that we will be talking. We could talk through the Zoom and then you can ask questions there, because like it's pretty hard to talk. No, it's not linked list, it's an array. So it is not obvious how to do this as an array, or linked list is much harder to implement rather than array. So let me create a new conference. Okay. Okay, so there is okay, let me. Yeah, I understand that return always the last element. I want to ask how to do this more. How to do it more precisely. Let me send you the link to the Zoom session. So Zoom session is here, so I send you the link Yeah, I mean lists and vector, yeah. Or like the standard arrays, like int something. I hope that I can hear you if you will come. So there is one person. Gabriel, do you hear me? Okay, I think I can hear you, but still not very clear. Okay, so the question is how to implement it on array. Array is typically like in Python there are lists. So like in Python you just create a like something like this 0 for x in range something like that, and for like C++ or Java for C++ it is like either like this with their full value or with the preliminary calculated length of the array, or vector. Vector A with some capacity also. And in Java it is int something a equals to new int of some size. So this is an array.
Oh, okay, but sorry, but there is any delay between the Twitch and the lecture in Zoom itself.
Yeah, I understand that that's possible, but I couldn't get it better.
Oh, that's okay.
I like Zoom is faster, and like the Twitch is on like 5 seconds I think later.
Okay. But I get it.
Okay, yeah, great. So how to implement the stack? The stack is implemented very simply. So you just maintain the top. Top is the topmost position that doesn't contain an element. So at the beginning, top at 0. So this is 0, 1, 2, 3. So push X, what it is doing, it is set stack top plus plus equals to X. What is doing pop? Pop is doing ans equals stack. Okay, let me write it even faster. Return stack minus minus top. So why it is correct? Like I specifically wrote this in the using special increment operations. Special increment operations. So this guy can be written as stack top equals to X and then top plus plus. What does it mean? What does it mean, this separation? That we takes the top, we set the stack at the position top to X, and then increment top. Like this separation is totally inverse. It says it at first, like we want to get top minus 1. So we at first minus minus top we are doing. So it decrements top and then takes the stack, the element of the stack. So this is equivalent to top minus minus return stack top. Okay, that is how to implement stack. I have the question for you. How to check that the stack is empty? So like
we have just to check top if it's equals to 0.
yeah, exactly. You just is empty. You return top equals 0. Yeah, great. Then, why do we need stack in general? Stack should be performed when given given operations push and pop. So you can answer these queries, but let's talk about the problems itself. So consider the problem of bracket sequence. So you're given a bracket sequence and you have to check whether this bracket sequence is correct. So what bracket sequence is? Bracket sequence can be created two times. Like this is one way to create a bracket sequence, and there is another. So to be more precise, it can be written like this. But generally, like a correct bracket sequence, either the concatenation of two correct bracket sequences, or it is the bracket sequence, the correct bracket sequence in brackets. So why are we talking about stack here? I guess that's the question that you are asking. But we will prove that if we consider the following algorithm, we just take a bracket and push it at the bottom of the stack. Then we take another bracket and push it in the top of the stack. Then we take another open bracket and push it at the top. Then we have a closed bracket. We just remove the open bracket from the top of the stack. That's kind of, we paired these brackets up. Then, again, closed. We see closed, then we should pop the stack, pop the open bracket from the stack. And so on. Then again, the closed bracket, you remove this open bracket here. Then you again put one open bracket, and then you get the closed bracket and remove it from the stack. And if the stack is empty, that means that we paired all the brackets up, and this means that this is the correct bracket sequence. Why it is correct? It is correct in the sense that when you have the concatenation of two correct bracket sequences, you can perform our algorithm on the first part of the bracket sequence and got empty stack, and then on the second one you got empty stack. And here we put open bracket, then we put the whole correct bracket sequence that return their kind of empty stack from here. So like you have an open bracket, then you perform S here, like the operation S, then it is removed, it returns empty stack, and then we have a closed bracket that removes the last bracket from here. So this means if the stack is empty, then the bracket sequence is correct, and vice versa. If it is correct, then the stack is empty. Okay, could you tell me probably how we could get rid of the stack in this task. Like using only one counter. Do you have an idea? Like without the stack.
We can just increment the counter with opening brackets and decrement with closing.
Yeah, great. So we have a counter that counts the number of open brackets, and if it becomes less than 0, then the bracket sequence is incorrect, and if it remains not 0 at the end, then the bracket sequence is also incorrect, so the number of open brackets is higher than the number of closed brackets. Okay, that's good. But right now we a little bit improve the problem. While the bracket sequence can consist of two types of brackets. We have open round brackets, like enclosed round brackets, and open rectangular brackets and closed rectangular brackets. So any ideas on how to solve that?
I think that it's by the same way. We have just to make a map between a curly bracket and a round bracket. No.
Okay, yeah, like kinda. It is definitely the same. So instead of putting only open round brackets, we put there a rectangular brackets also. So like at the beginning we have one open, we put here one open round and one open rectangle. Then we have rectangular one which is closed. We check, is on the top the correct pair? If it is not the correct pair, then our sequence is incorrect. So for example, in the case of like that, you have open bracket, closed bracket, open round, and open rectangle, and then we have closed round bracket. We just check the top. Oh, here is not the open round bracket, but open rectangular bracket. Then we have to say that their bracket sequence is incorrect. So you are performing, like you continue here, like you have the closed bracket, you remove the open square bracket, open rectangular bracket from the top, then you have closed round, you check that there is an open round bracket at the top, you remove it, and then you remove it again. That can be further improved for several types of different types of brackets. So for example, there can be curly brackets or like any other bracket as you want, but the key idea that you want to get out of this talk is that using this data structure, the stack data structure, you can check that any bracket sequence is correct. Okay. So that's it for that problem. However, now we are talking about the next problem. Is we can add an element to the stack. So x1, x2, x3. So like we have again push x, pop, and now we have an operation min. Min returns the minimal value on the current stack. So you have like 3 operations right now that you can do on the stack. You can push, you can pop, and you can ask for the minimum. Please note that we can ask for the minimum several times. and like we can ask pop several times and push several times, like as much as we want. The first question is, by the way, simple. What is the complexity of these operations of push and pop?
It's constant?
Yeah, it's constant. What is constant in the terms of big O?
O of 1.
Yeah, O of 1. Okay, great. So this is O of 1, this is O of 1. Now I want that the minimum will also be O of 1. So do you have any ideas on how to implement data, like such data structure? You can, like, I allow you to change the stack as you want, but still you have to answer minimal in linear time. So you can, not in linear, in constant time.
We'll have to also store the minimal while push and popping. Doesn't it? Like, instead of having just top variable, we also have minimal variable.
Mm-hmm. Where we store this minimal variable?
I don't know, maybe in the data structure or in the class that implements the stack.
Sorry. Okay. Let's take our. So we push 3, we push 2, we push 1. The minimum is 1. Okay. Like that's. Okay, let me do the following. Sorry. One moment. I will do the following. Where it is? Okay. I found it. Let me. I will do this, so like you will not have the delay for the Twitch. So you can look at the Zoom itself. I don't know what is the quality, but like you can see everything here. So suppose you put 3, 2, and 1. The minimum is 1, right?
Right.
You remove it. How do you where do you contain the minimum?
Okay. Maybe in another stack of minimum.
Oh, okay, in another stack. So let's. What it is doing? So we put 3. So we have 2 stacks, as you said. So the stacks for values and the stacks for minimum. So you put 3. What do you put in the minimum?
3.
3. Okay, great. Then when you put, for example, 2, what do you put on the stack?
Also on top of 3.
Okay, so you put 2. Okay, then 4 is coming. What do you put in the minimum stack?
I don't know.
Okay. I mean, you're pretty close to the right. To the correct data structure. It is pretty close. What you should put here, if you think about that?
Also 2.
Yeah, you should put also 2. So kinda your minimum stack will maintain the minimum, like the minimum of the elements on the stack that are below it. So like this 2 is the minimum for the whole stack. This 2 is the minimum for starting from the 2nd position, and 3 is the minimum starting from 1 position. And then when you want to ask please tell me the minimum. You just get the top value from the stack, from the second stack. And then when you pop, you take out this guy and the corresponding guy in the minimum stack. And you're still correct. So the topmost element in the minimum now will maintain the minimum on the whole stack. Okay, does it make sense?
Yeah, sure.
Okay, any questions? Will someone didn't understand? Okay, then we will continue. So we have a little bit more interesting problem. I will now explain how to solve it. Not I will explain. We will try to solve this problem together, and we will discuss if you cannot solve it and how to do that. So suppose we have a line of people. So we have a very tall person with height h1. Then you have a smaller person with height h2. Let it be a very small person. Then you have a little bit bigger person with h3, like there is some guy in the middle with h4 and etc. So you have and people standing. And people standing. Each person can see another person, like to the left or to the right, if there is nobody who is higher in between. So for example, this guy cannot see the small guy because there is a middle guy with height h3 at the middle. So it cannot see. It is not seeing like that. It is not doing like that. It is doing just the first kind of with this line swapping to the left. So it can see this guy, then it cannot see this guy because we can see only up to that point, and then we can see this guy. Is the problem understandable?
Yes.
Okay, the question is right now how to solve this problem. So we want for each person to understand how many people he can see to the left and to the right. So the question is how to solve this problem. Let's think a little bit and you can propose your ideas. Okay, any ideas? Probably you have come up with using.
I guess yes. Maybe for each person, we should have a stack and a mean stack to the left and to the right. So the minimum value of the stack. Oh, so after we process all the list of persons, we should count the every number in the stack that is bigger than the minimum.
No, that sounds strange, to be honest. You don't need me stack with the minimum in this problem.
Okay.
You just use their normal stack. Kinda you see that you can see these two persons here, and this you could think as kind of stack already. So let's maintain kind of the number of people. Like, let's maintain the people who can the person see on the left, and like just going from left to the right. So you can see at the beginning we have nobody at the stack. Then when the second guy is seen, we have like this, the first person. So we have this person. Then for the third guy you have like this person and this person. Then you put this guy in the stack and throw away everybody that are smaller, because we will never see them. So just you have the stack. Like let me draw the stack like in this way. So you have a very high person here, then you have this very short person here, and then you put our third person in the stack. You know that everybody who is small than it to the left will not be seen, because we can see only the person, like the first person with the height and nobody else. So we just remove from the top of the stack the small guy and put there the middle guy. And then the same, you put the fourth guy. We can see that the fourth guy is higher than this small guy. Then we will remove it from the top and put the fourth guy at the stack. So, and the number of people in the stack at the moment of our person will be exactly the number of people who can see this guy on the left. The same going from the right. You can do the same from the right. Can you tell me what is the complexity of this algorithm? Like the first question, is their algorithm clear? Do you have questions about it?
In order to, we have to maintain the smallest guy on the left and on the right, and we.
No, you go from the left to the right, and you maintain the people that can be seen from each guy. So you kind of add the new guy and remove everything who are not visible anymore.
Okay.
So any other questions? Like this problem will be in the homework. I'm not sure that if it will be in the obligatory tasks, but it will be in the homework itself. Okay. Can you tell me what will be the complexity of this algorithm? If you have n people standing.
I guess that it's O times O n times n minus 1 by O of n.
Okay, that's a very strong complexity. It's too much. It's too much. Can you tell me, how to calculate the size of the stack? In what time you can answer like the query size of the stack?
All of 1.
All of 1. Okay, great. Then, can you tell me how many times the person is put into the stack?
N minus 1?
No, each person is put in the stack only once. Because you're going from left to right and maintain the stack.
Okay.
You take one person and add it to the back while removing some of the guys. And how many times the guy will be removed from the stack then?
Only once.
Yeah, only once. So you add the guy in the stack once and remove the guy from the stack once. Then the complexity is...
What?
No. Like we have n people.
Okay.
Yeah, so the complexity is all of n.
Okay.
Okay, great. So that is about it with the stack. So let us continue with the data structures. So as you can see, stack is very powerful data structure. To be honest, it helps to do this tricky thing with maintaining the number of elements on the stack while going from left to the right. It's, for example, it is used in counting their convex hull, for example, of their points. There is also the algorithm also works similar. We just add a new point and remove every point from the back that do not satisfy our condition. So stack can be very useful in such problems where you know that you can add an element once and then remove this element once. And the complexity, of course, is very good. It is linear. So this algorithm is known as convex hull trick. Exactly because convex hull is working in a similar manner. Okay, now we are talking about Q. So Q is a data structure with 5-4 type. It is first in, first out. You can think of it as a standard queue of people or somebody else where you just join the queue and the first guy at the front is how to name it? The first guy in the array will be processed. Yeah, that's a good word. So you have kind of this array where you can do the following. You can add push and pull. I'm always like not very good with the notations because typically they're a little bit different from their stack notation. So we have push X and poll. So what push X is doing? Push X adds an element to the end of the queue, and poll, it takes the first element from the queue and returns its value. That's it. That's the whole data structure. So nothing really interesting here. Okay. So how to implement it? The problem is that it's not really easy. Аксоненко, hello Аксоненко, and hello hi Saiji. Okay, never mind. So we, like as you can see, this queue can grow infinitely to the right, and like it's removing from the left. So like let's start from the simplest implementation possible. We create a very large array with their length m, where m is the total number of elements that ever will be stored in the queue. And you will have two pointers, the head and the tail. So head points on the first element that is in queue, and tail will store an element that is like the first element that is not in the queue. So then how will we push implemented? Push X. We just say array A, like Q, let it be with Q. Since it is Q, let it be Q. Array Q. And we put it at the back, so we put it in tail, so we make tail plus plus equals to X. Then you have pop, or not pop, poll, which will return Q head plus plus. So you just return the first element from the head and increment the head to the right. So you can see you can never, like tail and head will never go out of M because the number of push is less than M in general. Okay, so what is the complexity of these two functions? Yeah, it is also constant, good. Like, I'm just checking that kind of, I'm asking stupid questions kind of here. I just want to know whether you're here or not. And how to implement is empty.
To check whether head equals tail?
Yeah, that's it. Return head equals tail. Okay, good. But what if the number of elements is really, like the number of pushes is really high, but we know that the total number of, like the number of elements in the queue at each moment is less than M? what we can do? Any ideas? So again, like let me rephrase the question. Suppose that we know that at any moment the length of the queue cannot be higher than m. What we can do in order to simulate the queue using head and tail and an array of size m.
Actually, the question is not very clear still.
Ah, it's not clear?
Yes, we should store the queue in the array. No?
Yeah, you're storing the queue in the array, but you know that the number of push operations is much bigger than m. However, you know that the number of elements at each time less than m. The question is how to implement the queue using an array of size m. Did it become clear?
Does it mean that we also poll, so number of pushes is high, but the number of...
Yeah, the number of polls is also very high. Yeah. I mean, since the number of elements of the queue never exceeds m, then the number of polls can differ from the number of pushes only by m at most.
Well, an obvious solution would be to just move the elements, but it's a complex operation. So reallocate.
Ah, you mean reallocate a queue to the left? Something like that. Okay, yes. That's one possible solution. However, we cannot do this in constant time. I mean, we kind of can, to be honest, but it is like the amortized time that we haven't talked yet. Like I wanted to talk about this like either on this lecture or in the second lecture, on the next lecture.
Okay. Maybe.
So so suppose that you have like this. So you have here tail at the end and head is here. So what would you say if I add another element where I could put tail?
Yes. Yeah, I guess we could make it circular to put it in the...
Yeah, exactly. We can make it circular. We just, when we reach the end of the queue, we just put an element here and move head here. Oh, tail, sorry. And you know that the size of the queue is never m, never bigger than m. Then we could have head and tail. They will be never equal. There is always will be empty spot here. So like it could be filled here, but here will be tail. So your condition, as you said, is empty. It still will satisfy only when the queue is really empty. And in this case, you can never override the queue itself. So you just have to do like that. Tail equals to tail plus 1 modulo m. And the same with the head. We just say head equals head plus 1 modulo n. Then let's talk, like, yeah, you can do this using the circular queue, as we talked about. But then, suppose that we do not know their condition on the number of elements in the queue. So this is not true. We don't know it. How we could implement queue? Any ideas? I mean, Gabriel already talked today about that. So we could do this in linked list. So we will have like some nodes that are connected. So not in the array, but some nodes that are connected together. And we have this node class node, that has the value and the link to the next. So here is the next, and here is the value. And that's it, kind of. You just maintain the head and tail. Then to add an element to the tail, you just say that tail, like, you create a new node, and equals new node of x, and then you say tail dot next equals to n, and then you say tail equals to n. You just create a new node here, create a new node with x, then set the next value from tail to n, and then you move tail here. The same goes with head. We just take the value from the head and move head to the right. You have to be a little, like, it's indeed a little bit too complicated, rather I talked right now, because it's better to use a dummy node so that the head is always empty, while if the next is null, then your queue is empty, and if it is not null, we just remove this and set head here, but their value is stored in the next itself. So you just always store some head to be sure that everything will work out. Okay, any questions about that? Any questions on how to implement the queue?
So far, so good.
Okay, great. Okay, we have not much time, but let's try, like, sorry, like, I understand that this was a delay in the start of the lecture, but still I want to finish in time. So there will be right now an interesting data structure. Is that you have push x, poll, and then you have to answer minimum. So again, as with the stack, we want to answer the minimum on the stack. So in this case, we will emulate our queue using two stacks. We have one stack and we have other stack. When you make push, so the stacks are filled, like we already processed something, we processed some elements, and then now we are asking to push X. Then you push X to the second stack, so there is the first stack and the second stack. We put X at the second stack. So here A1, blah 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 blah, AK. Then when we have a poll operation, we just take their elements from the first stack. So we remove this element, then remove this element, and then finally the stack becomes empty. And we are coming with poll operation. For that, what we are doing? This stack is empty, so we don't know whom to poll right now. So we take everything from the second stack and move them to the first stack, starting from the beginning. So like, after you move everything from the second stack to the first stack, we will have like that. We will have A1 on the top, A2 there, then AK and X. And then you can see that we kind of, in the second stack, we push the elements kind of in the wrong order. And but when we move from the second to the first stack, we push the elements in the right order. So everything on the top will be the first element that was ever pushed to the queue. The question is done. So is it clear how to emulate queue using two stacks?
Yes.
Okay, great. So the question is now how to ask for the minimum. Any ideas? Like we want to know the minimum on the queue. It's pretty simple. You have to remember itself that we can calculate the minimum on the stack that we talked today.
The same way that we had to create a third stack or not?
Yeah, you kind of, but we can do this in the same stack. Kind of, you maintain the minimum here, and you maintain the minimum here. Like like these two stacks will be two stacks with the minimum. Then the whole answer on the problem will be the minimum on the queue.
Getting the top of it.
Yeah, you just take the minimum from the first stack and the minimum from the second stack, and take and return minimum out of these two values. There is nothing hard about that here. Is it clear?
Yes.
Okay, great. Can you tell me, so suppose we did n push operations and n pull operations. So the stack is empty at the end. What will be the total complexity?
Two times n.
What times n?
2.
Oh, yeah, but 2 times n is what if we're talking about the big O? Yeah, it is just O of n. How did you calculate that?
Well, because we have n for push and n for pull, so 2 times n.
Yeah, but I mean, we sometimes like take elements from from the second stack to the first stack. I mean, you're right that it is all of n, but it is not so, like, it is not so trivial in the sense that we haven't talked, like, the problem is that each operation is not all of 1. That's a little problem. They're not all of 1. So I mean, push is all of 1, yes, but pull is not all of 1 because sometimes you have to move the whole bunch of elements to the left. I mean, here we can use the same trick as for the people who are standing in the row, because like each element is once put into the second stack, only once withdrawn, and once put in the first stack, and then once withdrawn. So each element has spent only 3. So put here, withdraw here to the first, like 4. Put here, pop here, push here, pop here. So it is all of n, indeed. But please, like, that's important. Pull is not all of 1. So what does it mean? It means that it is not all of 1, but it is all of 1 amortized time. What does it mean, amortized time? So suppose the operations are taking like these times. Amortized time is like this wavy times. Wavy. The time is amortized if t1 plus t2 plus tn is less than or equal than this amortized time. So for example, in this case, we know that the total number of operations is O of n, or some, it is less than c times n. And we can take that each operation costs O of c. So this is c times n, and if we say that it is c plus c, and they're equal here. So kind of amortized time means that we spread the whole time over all operations. So in total, they will be with right complexity. But in general, they're of different complexity. Like each operation is not necessarily will be of 1. It can be of n. But in total, like we can spread the whole complexity over n operations and call it amortized complexity.
Get it.
Is this clear, or you need some time, or do you have questions?
Oh, I have to study more about this theme, amortized.
Mm-hmm.
Amortized. Anyway, so, but I didn't understand what you just said.
Yeah, I mean the amortized time is just that you spread over all the operations and kind of divide by n, and that is why you get of 1 per each operation, but amortized. The interesting thing in that is that we can still emulate Q, but with 6 stacks, and do this in real of 1. That's an interesting algorithm. Like, it's really complicated, but we can do this. If you like, the problem with this algorithm is that each operation is not necessarily of 1, so you cannot write this algorithm, for example, nuclear station or something like that, because on nuclear station you have to return everything like very fast, and you have to be sure that each operation costs exactly constant time and no more. Like this algorithm, like you should, if you will program their atomic power plant or nuclear power plant, like please do not use them.
Okay.
Yeah, so the same thing goes for the problem that was with the guys who are standing. Each operation was also constant, but amortized, because like the total number, the total time to spend in the algorithm is of n, and we kind of made n operations there, so like each operation took constant time. So it is constant time amortized. Okay, and finally for today, I wanted to talk more about amortized, but we will talk about this next time. But today we will finish on Deque. Deque supports 4 operations. It is push front, push back, pop front, and pop back. So it is kind of their operations that are like merging their stack and the queue together. So you have kind of this array. You can push front, like to put element at the front. Then you can push at the end, put element at the end. Then you can pop front, you can take an element from the beginning, and then you pop back. You return an element from the back. I don't know about C++, but in Java this data structure is implemented, so it is named Deque. Exactly as that. So it is Deque integer. Or like some other type that you want to store inside. So it supports these 4 operations. So I have the problem for you. So you have a Deque. So you can push the person in the front, remove the person at the front, take element from the back and remove an element, like insert an element in the back and remove an element from the back. And you know that at each moment of time you can enumerate all the elements from 1 to n. And the question is, like you have these operations and another operation that tells middle, that returns their middle element, like at position n/2. So how would you implement this algorithm? How would you, how to solve this problem? So like you have to push front, push back, pop front, pop back, and take the middle element. in the middle of the current state of the Deque. Any ideas? Are welcome.
So, teacher, the question is how to implement middle function.
Yeah, like and
with only push from, push back.
Yes, yes. So you should implement a data structure that supports these 5 operations in constant time.
Okay.
I mean, in non-constant time, it is simple. Just go through the Deque and take the n/2 elements. So this is not very interesting, but I want to do this in constant time.
Okay.
Does the middle operation just return an element at n divided by 2?
Yes, you can do it, but you have to store it's not exactly, because if you think about Deque itself, they have like the left position and the right position that are taken here, and you have to take L plus R over 2. But it is a little bit complicated to implement such a stack or such a Deque when you have to decrement L sometimes and increment R, so like this array should be circular or something like that. So like a little trick is that we can use 4 Deques. Oh, sorry, for 2 Deques. So if you think how to do that using 2 Deques,
well, we should always keep a number of elements in both Deques.
okay, yeah. Oh, yeah. So yeah. Of course, we have like size operation, and we have there like left and right that returns the left and like we could store the first the left half in the Deque, in the first Deque, and store the right half in the second Deque. Then, when you add one element to the back, you just add an element and check. Should you move the middle element? So we always maintain that here will be the division by n/2. So we add an element, we check the sizes, and if necessary, we'll just take an element here and move it to the first Deque. So when you remove an element, you again check whether your split should be changed, its position should be changed, and you move like an element from the left to the right. Like you do pop back, push front. And that is how, and always their n over 2 element will be the, for example, the front of the second deck. Okay, questions? So yeah, this thing can be done in constant time, because you should move each time only one element in between here, because like the splitting point can move only by one. Okay, do you have questions about this lecture?
No?
Okay, great. So thank you very much for coming. Then we will end for today.